Welcome to the Smithsonian's National Air and Space Museum. This is our third installment of our new What's New in Aerospace series. Today we're going to be talking about communicating with humans in space. We have three experts from NASA with us this afternoon. And so we're going to introduce the topic by talking about the communication systems before we talk about scientific use of those systems and how they help us do science in space. So to lead it off, Mr. William Marinelli is going to talk about the Space Communications and Navigation Program. He's the manager responsible for the development of space communication and navigation projects, where we rely on the three globally distributed networks to do all the communications, the Space Network, the Near-Earth Network, and the Deep Space Network. Those three networks combine to service over 100 missions per day, meeting our current needs, and he's working on the development projects that will meet our future needs. His experience spans over 26 years of leadership in the development of ground and space projects for a variety of agencies. After serving 12 years in the United States Marine Corps, hoorah, Mr. Marinelli spent over 16 years in industry as a technical manager responsible for leading the development of a transportable ground communication system, and then moving on to several payloads that have operated on a variety of government satellite missions, including one payload that was hosted on India's Chandrayaan mission, developed and launched by the Indian Space Research Organization. Mr. Marinelli entered the federal government as a civil servant in 2004 and started his career in NASA in 2007. Bill?
Thank you. Thank you, Jim. All right. So, the slides up. All right. Let's go ahead and next slide, please. So, like any good person, the first thing I'm going to do is start with history, because we have to know why we got here. What this chart shows you is all the ground systems that we've had to use in our history. In order to look up at the sky and see these satellites go whizzing by, we have to be able to track them. And one problem is a good part of the Earth is ocean. So we've actually in the past had to use ships out in the oceans, we've had to use aircrafts, and those things are very, very expensive. And also, this is also very complicated to coordinate all these activities. As we think about a satellite, most satellites in the low Earth orbit take about 90 minutes, and then they come back close to that same area. So we have to constantly keep on telling these ground systems to go. So airplanes have so much fuel. The ships, we have to make sure they're in the right location. So this is a pretty complicated system that we had to try to fix. So it didn't cost so much, and also so we were able to get a lot of coverage. Next slide, please. So in the early 70s, we started noticing these things. The shuttle was first being conceived. It was signed to be approved, like I think it was 1969. And so the shuttle was starting to be thought of and how we were going to communicate with the shuttle. We're also seeing a lot of science missions that were starting to be thought of. And these things have a lot of data coming down, and they need to get it down fairly quickly. And it's really hard. If I look at that, the one thing in here talks about coverage. All those things, minus the ships and the airplane, only gave me about 25% at most coverage. So 75% of the time, I wasn't communicating with the satellites. That's not really acceptable, especially as we start looking at the space station as it is now. That's 24/7. We need to communicate with those astronauts. We need to get the data down from there in a reasonable amount of times. So we had to think of ways to do it. The TDRS was started around in the early 70s, but we also had some of these other, but the ATS-6, that had a lot of demonstrated kind of payloads on it. So they decided to test out the TDRS concept a little bit with that. And they communicated with the Apollo-Soyuz test and Nimbus 6. So next slide, please. So the original concept of TDRS, what they were trying to test out with these things, is we had two satellites well above the Earth's surface. And these are geosynchronous satellites. And what does that mean? It means they're about 35,000 kilometers up in space, and they stay stationary around the equator. Now, there's two things. If you see these little things that say TDRS West and TDRS East, if they stayed there, they would be geostationary. The thing is that we wanted to be able to go a little bit higher, so we put them in this geosynchronous orbit that does a little figure 8 around the equator. So it's able to see up higher on the Earth and down lower on the Earth, so we got a lot of coverage. So keeping them just there really didn't work. We still had a lot of blockage. But also, if you see, there's the two satellites, there's this zone of exclusion. And what that is we can't see it. So there was still a portion, maybe about 15%, that we couldn't see, but it's still, and especially now with station, that really wasn't going to be acceptable either. But this was the original concept. We had one ground system in White Sands, New Mexico was the initial concept. So where did we go from here? What did we actually do? Next slide, please. So in here, you see the outer ring, and those are the TDRS satellites. And we have, right now, I'll talk about the fleet a little bit later, but those stay and rotate with the Earth. So they're always looking at the same spots. And we just move the antennas around, and on the ground side, we also move around. In here, you see we had 3 sets around the Earth. Before I talked about 2. And the reason is we didn't want that zone of exclusion. We wanted to be able to see the entire Earth. But the one problem with that is the White Sands couldn't see all 3 of those satellites. They were blocked by the Earth. So what we had to do is come up with a station out at Guam, and that could then see those other satellites. And it could oversee a little bit of what we saw at White Sands, but it allowed us to have now full global coverage for our network. Also, in here, we see that the dot there is supposed to be the space station. Now, the one thing, it's really hard to draw and put on a slide what this looks like. But if I look at the altitude of the station, it's about like driving from here, Washington, D.C., to New York City. That's about how far away it is. How far is TDRS? It's like driving completely around the Earth. It's almost about the same distance. So it's much higher than that. So it allows us to have this big view of everything that we want to see and to maintain communications with the space station. And what do we get out of this with the station? Well, you figure we have constant communication with the crew. We know exactly what's going on with them. And we don't do it. We just take the data and send it to the flight centers, and they take care of the data. But they get all the vitals and information about the astronauts. They get to have the videos, the communications. I think if you've looked at our NASA website, there's actually an HD TV camera that you can go on there and look anytime, live TV, to see what the station is looking at. And it's really cool. But all that data goes through all the way up and then back down to White Sands, and then it goes out to our ground system, to our people operating the space station. So it's really a very interesting thing. The other is we have these other docking visiting vehicles. So when we bring up new astronauts, we have to rendezvous with the station and just park it into it. We need to make sure we have good communication so we don't hit it too hard. We do nice, gentle, docking with everything. And all those servicing vehicles where they bring supplies and all those things, all those communications go through our TDRS satellite. Let's see. That's it for this one. Next slide, please. So what was I talking about before? What was the coverage? If I looked at the ground systems just by themselves, you can see the green parts. Those are the coverage areas a ground system would give you. And what we see is the red tracks. That's what the flight path of the ISS looks like. And this is 1 week's worth of tracking of going through. So what we see is there's some green, but it's all centered around the land, and also we look at countries where it's not covered, where we don't have agreements to put our ground systems. So this really, if we're concerned about everything, we want to have 24/7 communication. This is unacceptable. So the next slide, please. So with TDRS and having all 3 satellites, 100% coverage. And now we do have reliability things with the networks, but our networks are over 99% as far as being able to get the data down and having issues. So really, we see 24/7 coverage with our communication satellites as they exist today. All right, next slide, please. So one of the things that do too is it isn't just ISS and it isn't just human space. And we'll talk, some of the people following me will talk about the science that we have not only on station, but on some of the other satellites. And we have Earth-observing satellites. We're looking at global warming, all those kinds of trends of what the Earth is going through. So a lot of those satellites come up to TDRS. Hubble, we've seen unbelievable amount of images coming out of the Hubble project that all go through TDRS. And it's really just fascinating science that comes out of this. Let's see. And that's it for that. Next slide, please. So just kind of to close up, what I was talking about earlier is we just launched 2 satellites, one in January of 2013, that was TDRS-K, and then January of this year, we launched TDRS-L. And so basically, you can count how many satellites we've had. We lost one in the shuttle disaster in the first and the Challenger, but was replaced after that. And we've decommissioned 2 satellites since then. The rest are still up there, and we are currently working on TDRS-M that will hopefully launch somewhere in the 2017 timeframe. So that's where we're at. I'm good. All right, thank you.
Thank you, Bill. Our next speaker is going to be Dr. Marshall Porterfield. He's the Division Director and the Human Exploration and Operations Mission Directorate, responsible for space, life, and physical sciences at NASA, where he oversees the human research, physical sciences, and space biology programs. This division includes management of extramural grants and research programs, as well as intramural research and engineering assets at 6 NASA centers. Currently, the programmatic focus is on ISS, or International Space Station. You see the beautiful model behind me, and development of the open science approaches. Dr. Porterfield is currently on a leave of absence from Purdue University, go Boilermakers, where he is a professor of biological engineering and founding director of the Physiological Sensing Facility at Discovery Park. During his career, he has worked on 5 shuttle flight experiments and flown 2 series of reduced gravity flight experiments. He has received numerous awards, including the Halstead Young Investigator Award from the American Society for Gravitational and Space Biology, and elected to the College of Fellows for the American Institute for Medical and Biological Engineering. His leadership includes service as president of the American Society for Gravitational and Space Biology, and was recently elected to serve as president of the Institute for Biological Engineering. So let's welcome Dr. Marshall Porterfield.
Thank you. Good afternoon and welcome. First of all, let me say thanks to the Smithsonian and National Air and Space Museum for hosting this event and allowing me the opportunity to come talk to you about some of the really important science that we're doing on the space station today. And we do have 24/7 communications with the astronauts. We use that as the foundation for all of our medical monitoring of the astronauts and the research that we're doing on the space station. And I'm really happy we're going to have the downlink opportunity following this event to demonstrate how we actually communicate with the astronauts. PIs at the universities and graduate students are actually doing the experiments with the astronauts on orbit because we do have constant communication. And it's a really powerful platform for research, which is really important because we're at a critical time now in human spaceflight where we're building the science that will allow us to secure our future for space exploration. So what is that future going to look like? I love these artist renderings. I think people get inspired when they think about what we're going to do in the future. Pioneering the moon, exploring the moon, doing science on other bodies like Mars. So communications actually is an issue with Mars. We have robotic rovers, but there's a communication lag. We don't really interact with those robotic systems in real time. So we need autonomy in terms of exploration. And I believe that the human is going to be the explorer of the future to facilitate discovery. So what is it going to take for us to get there? There's some critical science issues. I'm going to talk about some of the science that we've done. We spent 10 years of assembling the International Space Station. We've had humans in space continuously for 14 years now. But only over the last 4 years have we really had it put together to the point where we're operating it as a laboratory. So it's the most advanced laboratory ever built, flying 270 miles above us at 17,000 miles per hour. An engineering marvel in itself, a tremendous platform for future discovery. So at this point in time, we've really ramped up our research, and we really have invested heavily in research capabilities. Today it's fully assembled, and it's our time to utilize this platform to do the science that we need to do. So what is the science that's important? So if you looked at the first slide and showed a lunar module, there's physical systems like plumbing and water flow that we have to take care of. But here we are now today, and the most important issues are human health and astronaut and crew health. So we're developing new types of technologies to do monitoring, biomedical monitoring on orbit. That's important for ongoing medical operations, but we fund a great deal of basic research, discovery-based research, and human biomedical systems at many different universities. Nutrition is important, countermeasures for bone and muscle wasting. Literally every organ system in the body is affected by exposure to microgravity. Radiation is going to be really important. Right now we're protected by the Earth's magnetic field in low Earth orbit and ISS, but when we move out to the Moon and Mars, the radiation environment out there is really critical. So that's one of the critical things that we need to address in research now on the International Space Station and also on the ground. Nutrition, food storage, nutritional quality of foods, vitamin content of food is reduced in microgravity or during storage. So the astronauts are going to require potentially a fresh food source. So we're actually doing research now using a flight system called Veggie that was developed out at Kennedy Space Center. It was launched on SpaceX-3, and we recently, Commander Swanson harvested a crop of the first lettuce grown on the International Space Station. We're bringing that back on the next SpaceX landing, and we're going to analyze that to make sure that the salad is safe for the astronauts to eat, so there's no contamination of microbes. Microbes are and microbiological systems that we carry with us in our body are really important to human health, it turns out, and we have numerous studies have showed that microbes become virulent in microgravity. They have a tendency to become more aggressive in terms of their potential to cause disease. At the same time, the human immune system is depressed in microgravity. So it's not just the bone and muscle unloading issue, which is really critical. An astronaut can lose bone over a month period that's equivalent to an advanced case of osteoporosis over a year. So we've been finding that people are healthier on the ground if they exercise more, and actually that's part of the regime that we're developing on the International Space Station. Equipment to allow for weightlifting and running. The astronauts do about 2 hours a day worth of exercising, and then we found that does reduce the impact on the muscle and skeletal system. Cardiovascular function is affected. Neurological function is affected. Because of the fluid shifts in the body and intracranial pressure, we think that's affecting vision over long periods of time. So if you think about what that future mission to Mars is going to look like, it's going to be a year, maybe a year to get there and a year back. We want the crew to arrive healthy enough to be able to explore Mars and then get them home safe, protect human health. So right now is really a critical time in the history of human spaceflight, I believe, because we are advancing the science that allow us to safely and affordably explore in the future. So the investments that we've made over the last over 10 years of building the International Space Station and now to continue to operate it are actually really critical. And so, and that includes a lot of other logistics in terms of this, supporting the science is, communications and transportation are critical to that too. So the main countermeasure for bone and muscle is really involves exercise. And so it reinforces, I think, what we need to be concerned with in terms of our health on the ground. There are a lot of spin-offs, and the act of exploring space and operating the space station as a laboratory and of supporting science on the International Space Station actually accelerates innovation. So a lot of the things that, new technologies that get developed, a lot of new approaches that get developed are done so because of the challenge of exploring, the challenge of pioneering space. So I think those challenges are important for us to take on because they push us to do new and better things. I remember when I was a boy, being in my backyard. We lived in Jacksonville, Florida, and saw one of the Apollo missions. You could see the flame going across the sky. That's all it was. It was like a flame across the sky. And I remember over the next few days watching that on TV. And it had a great impact on me in terms of inspiring me to go into science and develop the career that I have. But it's accepting that challenge of space exploration that's important. So we're at a critical point again. I can't stress that enough because if we don't buy down the risks and develop the science to safely explore in the future, now that we have the space station, we may not have that opportunity in anytime soon again. So we're really at a critical time. And again, I think that it's important to inspire and accelerate innovation, to inspire kids to become interested in science, technology, math. But we need to do more than that right now that we have the International Space Station. We need to enable and equip the future of space exploration and a future for our children in exploring space. So thank you very much for your attention.
Thank you, Marshall. And now our third speaker will be asked up. It's Dr. Stephen Volz. He is the Associate Director for Flight Programs in the Earth Science Division at NASA headquarters. As such, he's the Program Director for all of the Earth Science flight missions and associated activities. This includes 17 satellites currently operating in orbit, 10 satellites in formulation and development, and several more missions that are in the early design stages. So let's welcome Dr. Stephen Volz.
Thank you, Jim. And thank you, everyone, for coming here today. I really appreciate the opportunity to present and talk to you about the work we're doing in NASA from the Earth science perspective and science in general. You've heard excellent presentations about the communications from space and also from Marshall about the manned space flight and the value of manned space flight to the exploration to the moon and to Mars and beyond. I'm going to take a slightly different tact and talk about the value of robotics and about measuring, making observations from space. As you can see in that the picture of the image up there, the ISS is a impressive engineering platform, but the value of it to science and the researchers are the location it has and the resources it brings to us. So if I can see the next slide, you'll see in the presentation here, the ISS in the vantage point from space, it provides us as a platform for making observations. Now, why would we make observations from space? We can check the weather by looking out the window, et cetera. But from an orbiting standpoint, we get to look at the whole Earth as a system. And that is really essential to understand how different parts of the system, the clouds, the ocean, the land, how they all interact. And we need that global perspective from space. The ISS provides a unique capability there. As I said in the intro, we have 17 different satellites orbiting the Earth continuously, but they orbit from different times of the day, from different altitudes and different perspectives. The ISS has a certain capability. It is very large, as you can see. It provides resources that we can use. We don't have to build on our own. It is in low Earth orbit, very low. And if you look at the image over here on the right, this is sort of what the Earth looks like from the ISS. So it's relatively low, that 200 miles or so above the orbit. So you can get a very good view of the Earth from that low altitude, and we take advantage of that with the ISS. It doesn't do everything. It doesn't go over the poles because we're in a low inclination orbit. So if I'm looking at mapping ice, this is not the place to do it. But it does do other things. It maps the Earth at different times of the day. So I can look at weather in the morning versus the afternoon. And whether in the morning, if you're measuring the soil moisture, for example, you might have dew on the ground. If I only looked at it in the afternoon, I would never see that. So the ISS is complementary to the other measurements we have. On the next slide, we'll show a picture of what we have currently planned for the ISS in terms of Earth observing instruments. What Marshall was talking about was a lot of the research going on inside the station. Well, that's great on the inside, but we like to stick things on the outside because then we have the perspective of looking at the Earth. And you can see here, and you can see in the model over here, there are lots of attachment points on the International Space Station that we use for putting different instruments up. And I'll talk about each of these a little bit at a time. But what do they do? We have those on the underside, as you see, like CATS, EcoStress, and JEDI. They're on the underside of this part of the platform, so they're great for looking down, or we call nadir viewing. So if we want to look at the Earth, we can stick stuff on the underside of the station there, use all the resources, the data downlinks, the power, and just stare at different spots on the Earth, and it's very capable. And if you want to look up, like some of the astrophysics and other ones, you can put things on the top, and you have a very good view of the galaxy, of the universe, as it goes around the Earth, looking up. And there are different aspects that are useful for different measurements. We take advantage of all of those by designing our instruments to match. On the next slide, we'll talk about the one instrument called the hyperspectral imager for coastal ocean, which was launched in 2009, is one of those looking down instruments. And a hyperspectral, what it does is it takes multicolor images of the Earth, and it's optimized over the wavelength, which indicates certain biological functions in the oceans. It is sensitive to plankton and to different chlorophyll in the ocean. So if you take a very detailed image of the Earth using the HYCO instrument, you can see where you have algal blooms in the water. You can see where water is clear or dirty or turbid, as they say. And by looking at it in the hyperspectral frequencies like that, you can distinguish different kinds of growth, different kinds of biological functions going on in the coastal oceans in a way that you can do with an airplane, but only a very narrow range. From the ISS, and go in the next picture, you'll see you get large pictures of this wide swath, and you can look at any place on the Earth that's covered by the ISS, and with these multiple pictures and with very detailed analysis of the data that come with them, you can pick out features that are environmental, biological, pollution or air quality, water quality features that are hard to pick out, or you could with lots of airborne, but it's much more efficient to do it from space. And the ISS has been providing this for like 5 years now with the HYCO instrument. Another example is the we call ISERV, which is a Severe Environmental Research and Visualization System. SEVERE is a program that we've had within the Earth Sciences Division, which allows local communities, whether in Africa, Costa Rica, we have another one in Asia, to take advantage of global perspective from orbit to do disaster management, to do impact assessments of things that are happening, like there's a flood or there's an earthquake or a mudslide. The local communities around the world don't all have great resources to send airplanes, et cetera, to map it and understand what happened. With the SEVERE program, that's a NASA program which takes up satellite data and pipelines it and makes it appropriately usable to the local communities. Well, this is an adaptation or an enhancement of that with using a commercial camera attached. This is actually inside the station looking through the optical window called the wharf. And it is pointable. So if there's an event that occurs, the SEVERE instrument, the camera, the ISERV camera, and then the next overpass can target and move back and forth and take near real time or rapid response pictures of these events as they, right after they occur, to allow local researchers and actually disaster responders to assess damage, to know where to go, how to address it. You see on the next page a couple of pictures. The upper left there, if you recall, last summer there was some significant flooding in Calgary. And this is only one picture. If you take a follow-up picture from before and after, and they do map comparisons, they can see the regions that were flooded. And they can pick it out right away, and they can tell the local responders, you've got flood areas here or there, and it's very useful for deciding how to allocate resources. And the fact that it covers the Earth, or is at least between plus and minus 50 degrees, allows you to do this response all over the globe, wherever the things may occur. Now, the alternative would be to fly multiple satellites, which can provide this on a regular basis, but that's much more expensive. This is targetable and directionable, so it really is useful for that niche, that application in the near time. On the next slide, We have another one called the Rapid Scat, which is on the ISS. Rapid scatterometry uses a method of active radar. It bounces a radar signal off the ocean and checks the return. And it's been measured over time. We know from practice that the surface roughness of the ocean is an indication of what the wind is like right over that place. So by correlating the roughness of the ocean with the return signal, you can measure winds. And this has been used by NASA satellites and other satellites for many years, and it actually goes into our numerical weather forecasting and our weather programs. Scatterometry is an active approach. On the ISS, click one on this one, you can see. This was launched just a couple of weeks ago, and the value, again, what the ISS does, most of our orbiting satellites pick a particular time of day. So it's a 1:30 crossing time over the same time of day every day. But the ISS, by moving from periods of times of day, you can see morning winds and afternoon winds and tell the difference. You can see how it varies over the night times, et cetera. And it's a good complement for those stationary orbits, which always look at the same time of day. And on the bottom right, you see a picture there of the first image that came out of RapidScat, which I said was launched on, I think, September 21st, installed a week later, and these are data just from last week. And it's up there now. And go on the next slide, and we'll see. We'll skip this one. It's a little picture of the details of it, but you get an idea of the scale. And this is an image showing how, this is sort of I'll walk through this a little bit. Getting to space is half the challenge, or there's 3 halves to this challenge. The second half is actually getting it from the rocket and installing it on the space, and the third part is actually operating it. So there's lots of steps, as you can see, in getting something from the rocket. That's a Dragon capsule from the SpaceX. They have multiple manipulating robot arms. You see examples on the model here. And they take it, rotate it, and install it up on the space station. Leave that up for a moment. And there's some assembly required, as we would say, because it's complicated enough that you can't fit it all into one. But the engineering capabilities of the station allow us to take pieces, assemble them robotically. No astronaut internally doing this. Is all operated from ground control to make the installation occur. And this takes about a day and a half to do. It's not simple. That was much faster. It takes a couple of hours. I think it was about 3 hours to get the first part, and there were 2 parts. This had to go up and assembled in space, and another 2.5 hours to get the second part to plug them together. Once you plug them together, though, go ahead to the next slide, we have our rotating antenna, which is this radar dish, which sweeps around every minute or two, and that gives us that radar antenna signal, and it looks for the reflected surface waves from the Earth. So this data were just from about a week ago, and it's now operating on the space station off the Columbus module, one of the external platforms. Go to the next slide. And that's just 2 that we'd mentioned 2. iServe, that are up there now, iServe and HICO, and RapidScat just installed. We have a number of other ones planned for the future. CATS is one. It's a cloud aerosol transport system. It's a LiDAR, which is a laser range and detection. The station, again, has a lot of power, and lasers take a lot of power. If I had to build a satellite, I'd have to add a lot of stuff to it. It would be expensive. Station is just like plugging into an outlet. It's an expensive outlet, and it's more complicated, but it provides those things I don't need to worry about. So what the CATS LiDAR does, it shines a laser down, and you actually can sometimes see it when it gets up there next year, or at the end of this year, and the reflected light bounces off aerosols in the atmosphere. Aerosols are dust and particulates and other things. And by measuring that aerosol content, you can tell how pollutants are moving, how winds are moving, what's going on after a volcano, for example. You remember the Iceland volcano caused significant problems and disruptions. This is sensitive to those particles that are in the air and allows us to measure that and see it in real time. This is a relatively efficient way to do this using commercial parts because the station's in a low orbit. It can handle commercial parts. And click on the next slide. You can see a picture of it. That's about phone booth size, for those who are old enough to remember phone booths, instrument. And it weighs about 500 kilograms, have several hundred watts. And this will go up at the end of this year, and we hope to operate for a couple of years off the Japanese experiment module. On the next slide, you'll see another example. So I'll make a slight transition now to astrophysics. We talked about looking down, which is looking down at the Earth. But now there's another half of the station which is looking up. And the station is being used now for those uses, for those utilizations. Right, upper left, you'll see the AMS, which is the alpha magnetic spectrometer, which is a cosmic ray experiment. It's been flying for several years. But we also have a couple of others planned. And we'll click on the next one. You'll see one is called the ISS CREAM, which is another cosmic ray detector. It's big and heavy, which is the only way you can absorb cosmic rays. It's going to mount right next to where that CATS was, so multiple boxes can fit different things. It just sits there and absorbs cosmic rays. And it will be able to measure the cosmic ray spectrum, which in ways that we haven't been able to do from space before. And the next one is a different example. It's called NICER. This is kind of cool. You think when you fly a satellite like Hubble or others to do astrophysics, you like to be able to stare at something for a long time. And that's the essence of long duration observations. Now this is an ISS, it's moving around a lot and it's torquing and it's twisting. So making an astrophysical observatory on that platform is kind of like trying to put a telescope on a boat, it seems like. It's not, you wouldn't think it's intuitively the way to go. What NICER is going to do is look at neutron stars and look for neutron pulses. And actually one of the applications, there are multiple applications just understanding what neutron stars are, but one of the applications may be as a sort of a galactic GPS, because we know the timing of these neutron stars, and they're so perfect. If you know the timing between 2 or 3 of them, you can locate yourself in space by the differential arrival of those different signals. But what this is going to do is understand how those signals work. I mean, how the neutron stars work. So if you click on the next one, you'll see an example. So what happens, this is sitting on the top of the station, and it wants to find a neutron star. So as the neutron star comes in the field of view, you can see it tracking here to the right. The field of view is that grayed area, and the target is what you're looking for. Now it's grabbed onto the target. So what the electronics, what the mechanisms do, it allows the instrument to track that target while the station's doing all the stuff the station does. And you can actually get long-term observations from a very dynamic moving platform by the appropriate star trackers and mechanisms built into the system. And that's what the NICER system is going to be able to do. And again, in a way that would require a much more expensive, much more complicated approach than just taking advantage of the station and just putting in a tracking and a 2-axis pointing system to go along with it. So next slide is sort of the summary of what the different ones that we see on the station. You see, we've got a bunch of others I didn't mention, such as EcoStress, which is going to look at the thermal infrared radiation from the Earth, looking for moisture. JEDI is going to measure forest canopies from space. There are a bunch there. I won't go through them all, but multiple applications, multiple instruments that we have planned for the next. These are just the ones going up in the next 3 to 5 years, and utilizing the capability of the station and the downlink and the platform and all the investment we've already made to really make an impact on our understanding of the Earth and of the universe too, through our astrophysics experiments. So with that, I thank you, and I turn it back over to Bill. Okay.
All right, thank you, Steve. One of the things that I like about the NICER experiment that he was just talking about, which is looking at X-ray stars, is that there are some of these X-ray stars that spin at very high rates, hundreds of times per second, hundreds of revolutions per second, and give off huge jets of particles that we can detect. That we call those pulsars, and they give us actually timing sources, and with precise knowledge of the position of the pulsar in the sky and the timing source from its rotation and the particle jets, X-ray pulsars can act as the equivalent of a GPS satellite system. GPS, we put satellites up that emit timing and position signals. That's how we get position here on the ground. Well, it turns out the universe gives us free time and position through the universe through these pulsars. And so this may be the forerunner of our first genuine interstellar capable technology that would help us travel between the stars. So let's invite the speakers back up for some question and answer. And Beth is going to be here with the microphone to let you come up and ask your questions. Do we have some from the... We're also getting questions from the audience on the webcast.
Yes, we do. We actually have 2 questions from one of our online viewers, Tim. Dr. Porterfield, what are the advantages of using humans instead of robots in exploration?
So when we're doing research right now on the station, we can do that with automated systems. There are some, especially in the physical sciences area, and doing combustion research, which the demonstration we're going to have after this is going to be a live experiment. It's not a demonstration. It's a live experiment. The advantage of that of using astronauts to do that type of research is that you can respond to things that you didn't expect to have happen. I mean, when we're exploring and moving out to new environments, you always encounter new challenges that you didn't expect. And so the ability to be able to adapt, a robotic system can be set up with some level of autonomy, but usually outside of what was originally anticipated, it's very hard to be responsive and have that kind of real-time capability. So the human exploration is critical in that way, because we don't really know what kind of problems we might encounter or so you need intelligence built into your exploration.
And also from Tim, Mr. Marinelli, why don't we have a land communication system in California?
Right now, what we have here is just what we're using. There's communication centers for other organizations, other agencies, but what we use for TDRS is right there. We do have our Goldstone, our deep space network antenna we have out there. So we have antennas, but what we use for these particular missions to support the ISS, we use straight out of there. We want really one location, the two locations, because the cost to keep updating and upgrading multiple stations is really not tolerable. We need to try to keep our costs down, but we do have antennas in California for other missions.
And as we're working on optical communications with lasers, we also have telescopes in California, for example, on Table Mountain that we're using. So there are a number of stations and facilities in California, as well as our resources scattered around the world and in space.
Okay, so those were our online questions. Does anyone in the gallery have questions?
What will we learn from a lightning imaging sensor?
The lightning imaging sensor, or the LIS, is lightning is a pretty important atmospheric process. It's a measure of energy content in the atmosphere. It's actually obviously it's linked to the initiation of forest fires. It's an indicator of other massive important storms, tornadoes, or et cetera. So the presence and the magnitude and the frequency of lightning is an important input parameter into various numerical weather modeling activities. We've been flying lightning mappers on various satellites. We have one now on the TRIM satellite, which measures precipitation and lightning, because storms and lightning go together, so there's value to that. We're actually flying one on one of the NOAA GOES satellites called the GOES-R, which has the lightning sensor from geostationary. Geostationary has less resolution, so it's a larger footprint. They won't have the precision. So by using it from the ISS, we'll get all the features of the precessing orbits at different times of the day, but we'll be able to understand better how lightning correlates with storms, with weather processes, and just as for fire detection and monitoring. When you have lightning, you're likely to have ground fire. So if you have a drought area and you measure multiple lightning bursts, you may not have people around there, but you'll know there were 50 lightning strikes in that area in that period of time. You may want to have a flyover to see if there's something you need to follow up on.
Will we learn these jets or these lights that go up into the space from learn about those?
I'm not an expert on the upward bursts of the lightning, the sparks, and the high energy pulses. This measurement won't, but that is certainly something that's been observed by astronauts and by the station in general, and I'm not sure if we have any instruments specifically designed for that, but it is a pretty interesting phenomenon we've noted, and I don't have the background on my own to speak to it more.
Okay. Marshall, do you have examples of how the research being done on the space station, particularly that applying to humans and the precursors, like the rodent research facility, is going to translate into improved medical capabilities here on Earth for human health improvement?
I think anytime we pursue fundamental discovery-based research, we find things that that have application, that spin off. And that's one of the things NASA's always struggled with, is communicating the value of the spin off of the research that we're doing. Definitely osteoporosis and conditions associated with aging are going to be improved by what we learn about crew health and how to protect crew health. Really, the experience, the phenomena associated with microgravity and how it affects human health is really analogous to advanced aging across every organ system in the body. So, and there are 30 specific risks that we map in terms of the human research program, and we build research programs around those individual risks, and they have direct application and have in the past, in many ways, contributed to the body of knowledge that advances our medical capabilities and our health systems here on Earth.
So is it true that the human immune system response is also suppressed or reduced in space?
Yes, it is, and it's that's very worrisome to us because at the same time, microbes have been demonstrated to become more virulent. So the human immune system is reduced, and microbes that we carry with us that have the potential to act pathogenically may become virulent. So both of those things go hand in hand.
And pharmaceuticals seem to have a shorter shelf life and reduced effectiveness. It's sort of a trifecta of bad things in space.
Yeah, you're getting old, you're going to get sick, and your drugs aren't going to work.
So we've got some serious challenges in figuring out how humans are going to live in space.
Yeah, we really do, and that's why the window of time that we have the ISS, this platform to operate it as a laboratory, is so critical to the future of human exploration. And there's lots of examples in the physical sciences too, where we're doing the science that will allow us to engineer more advanced systems to operate microgravity more efficiently and more cost effectively. But definitely too, the human health issue in terms of human exploration, we need to really take advantage of the opportunity we have on the ISS. We have an upcoming one-year mission that's going to launch in 2015. Scott Kelly was selected as the astronaut, and we have also a cosmonaut. There's 2 men. They're going to spend a year in orbit. That's going to give us some more data out for longer periods of time. But the great thing about Scott Kelly being chosen is his brother Mark is twin. So we've commissioned a set of investigations, 10 investigations that are all coordinated. It's called the twin studies. And so we have genetically identical pairs, and we're going to be taking data from both of them longitudinally throughout that year to see how this individual changes. And we're going to use the most advanced genomics technologies that are available now. So really ramped up our technological and biomedical analytics in order to take advantage of that opportunity.
Well, thank you very much. Unfortunately, that uses up our time available today. I'd like to thank our 3 speakers, Dr. Marshall Porterfield, Bill Marinelli, Dr. Stephen Volz, all from NASA. I'd like to thank the Smithsonian National Air and Space Museum for hosting us here today, and our sponsor, which is Boeing, for this What's New in Aerospace series. So thank you for attending, and I hope you have a good day at the museum.